does peak and has any relationship with the value of an? But do you think, because peak is a relative thing, right? Peak is all greater than equal to. Even if you decrease all an by minus by the maximum of the all the an, still it will hold, right? So what they're asking is that if an is a peak.
Hello, guys. Welcome to Cheenta School of Statistics and Data Science. We are a team of extremely passionate teachers, researchers, and statisticians from the top universities of India and USA.
So if you observe, it's written that a sequence of real numbers. What is a sequence? Let me define that. It's nothing but a function from natural numbers to real numbers. So what does it mean? Um, so this means that a function is nothing but a mapping. So if you do 1, 2, 3, dot dot dot, and n, like it continues. So you're assigning each real number to this, which you call a1, each real number to this, which you call a2, or f1 or f2. You're assigning, like, it's a mapping from this natural number set to a real number set. This output is, you are calling this like this. So this together, a sequence is represented as like this, when n is greater than equal to 1. This is how it's represented as, right? And that's what you are seeing here. Now it's saying that an has a peak at n if an is greater than equal to ak for all k greater than equal to n. So it's saying that an has a peak at n. This is n. So an is a peak at n if an is greater than equal to ak for all k greater than equal to n, which means if you consider all the subsequent n plus 1, n plus 2, all the numbers, all the points. So if you draw it geometrically, it will look like this. This is the f of f, the sequence, and this is the n, rather I should say x. So it's nothing but here is 1, here is 2, here is 3, 4, and dot dot dot. So each one is a point. It's a sequence. So it's saying that it's n is a peak if all k greater than equal to n is less than an. That means it's like this. All of them are less than this. It can be oscillating, but it's less than this. Okay. So that means still after this is the highest point in some sense. It will not go above it. So a k is less than equal to an, or is it less than or less than equal to? It's less than equal to n for all k greater than equal to n. So it's saying that this is this. So now it's asking it's giving you three statements and asking you whether they're true or false. So let's understand each of these statements in details. So it's saying no sequence of real numbers can only have can have only finitely many peaks. No sequence of real numbers can have only finitely many peaks. So what it means, let's understand in details. No sequence. So it's like, let's not write it. So finitely many peaks, finite number of peaks. That's what he's asking. Let's understand what it means, finite number of peaks. So finite number of peaks means, let's assume that there are finite number of peaks. Let's assume 2. Okay. So whenever it's like finite number of peaks, whenever they are saying you like finite number of peaks, it can be 1, 2, 3, 4, 5, 6, anything, right? So we'll start with an easier option to start with. Why an easier option to start with? Not like it's a proof, but it will help you understand the process that is happening under, right? So that's why it's the, so always start with an easier problem, easier example to start with. So let's take one. Let's take one because that's the easiest one. So let's say it has a peak at 5. That means it can happen whatever. It has a peak at 5. That means there is a thing. That means it doesn't have a peak at 1, 2, or 3 or 4, right? So what does it mean? It doesn't have a peak at 1, 2, or 3, or 4. So what does it mean? It means that for each of these numbers, there exists a number after this which is greater than that. Otherwise, it would have been a peak too, right? It's a tricky thing. You may think that 5 is a peak, therefore anything can happen here and it will be it kind of less than this height. But that may not be true, because if this is happening, this is also a peak at 4, right? So therefore, you have to be careful. If it is one peak, that means the previous numbers should not be like the largest. You understand? Should not be the largest. There can be more nuances. For example, for this, it can be less than here, but there can be a number bigger than this here, okay, but smaller than this, the actual height, the actual peak. This is a max. But understand that since this is a peak, no number before this can go above this, because then it would have also become a peak. but we have only one peak, so that's a contradiction. So therefore, do you agree the peak is the maximum height? If there is one peak, that's the maximum height that our sequence can achieve, right? So I hope all of you understood this. So now let's see what happens if there are two peaks. Let's see the criterion. So we will now understand what happens if there are two peaks. So one peak, we have understood that one peak is, it's kind of the max point, unique maximum, because if there is another point that is taking that value, that value is also a peak. So it's like unique max point, that is the peak point. Now let's see what is the process when there are two peaks. See, what I am teaching you, or rather sharing, not teaching, what I'm trying to make you understand is that you can also do this if you just give time to it. You have to just give some time initially and understand step by step what's happening. So let's say five is one peak and 3 is another peak. Okay. So if 5 is one peak, that means everything after that is less than this, let's say. And here also everything. So since A3 is less than A5, if A3 is like, if 3 is a peak, that means this should be less than this, right? Less than equal to this, right? And of course, the rest of the things are less than equal to this, and the rest of the things are less than equal to. So this is A3, this is A5. So of course, you can understand A3 should be greater than equal to A5, right? And everything between A3 and A5 should be, uh, I mean, it can be also here like this. It doesn't matter. It can be like this also. Okay. Doesn't matter. It can be less than A5, greater than A5, doesn't matter. And of course, A5 is greater than equal to everything. So you have to just make sure that these things are less than equal to A3. Okay. The rest will be taken care of because A3 is greater than equal to the other things. So what it means is that if you have two peaks, that means the earlier it is, the more max it should be, right? And you can give anything less than this here. One important point is that it cannot be in between this. A4 or A3, rather A4 cannot be larger than A5, right? This is very important because if it's larger than A5 and less than A3, of course, less than equal to A3, then that is also a peak. But we have only exactly two peaks. So this is where the interesting things happen. So you are understanding the process, what's going on. So it's like you fix 2 points and then you can manage the other things, right? So the question is that no sequence of real numbers have only finitely many peaks. So can we? So this will be true. This will be false. So we can see that probably we can make up two peaks, right? It's very easy, probably. Like an example, let's say you can just make 0 0, or you can just make 5 then 3 and then all 0 0 0. Not all 0 0 will not be an option, because if all are 0 0, then every 0 is a peak, right? So what if we do like this? So therefore the earlier it is the maximum possible, that we have understood. So what if it's something like this? Let's say let's say you have to make finitely many peaks, right? So what we do is that we make some constant values. Let's say k peaks, 5 peaks. We need to make 5 peaks. So what is the way to make 5 peaks? So we make constant values, all of them maximums, and then for all of them, like the 6 7 onwards, what will happen is that they have to be, understand, they cannot be decreasing, because every decreasing sequence is a peak, will be a peak, right? For every decreasing sequence it will be a peak, right? That will be a peak. So it should not be decreasing. If it's, can it be increasing? Yes, it can be increasing, sure. So increasing to what? So increasing in such a way that it is less than equal to this. So increasing will never be a peak, right? Any increasing sequence will never be a peak. So therefore, this is the first observation. Any increasing sequence can have no peaks. So can there be 0 peaks? Yes. So that's the first question we missed. See, we could have gone more fundamental. Can there be 0 peaks? Yes. Can you give an example? Increasing sequence. So increasing sequences have 0 peak. So now, and decreasing sequences will always have infinite number of peaks. Decreasing sequences have infinite peaks, not finite, at least. So that's a good thing. We have found infinite peaks and 0 peaks. This is called extreme value problem. Like in in other sense, you're trying to understand what happens at the extreme. So number of peaks. So that's how you organize your knowledge, whatever you have gathered. Example. So 0 peak you have understood, increasing sequence. Infinite peak you have understood, decreasing sequence. Right. Now we have to understand about. So let's see the options now. I think so. There is options about infinitely many peaks. The option about finitely many peaks. and some property about having finitely many peaks, right? So let's understand therefore what finitely many peaks mean. So first of all, can there always exist a finitely many peaks? I think answer is yes. So it's like, let's say, can you make any k length k peaks sequence? It's very easy. What you do is that you know that so what you want k peaks, and you do not want any other sequence after that, any other sequence element after that have no peaks. So what you make it increasing such that it doesn't go above this bound. And the easiest k peak is that, as Megha has already shared, that peak has something to do with upper bound or the maximum value. So what we do is that we make the first k points, a1, a2, ak, same value. Let's say capital M. Okay, same value, capital M. These are all k peaks only if all the points after this is less than equal to the M. And how do you make and you want none of them to be what? None of them to be peaks. So what do you make? And you know how to make no peaks by making an increasing sequence. So you have to make an increasing sequence which is upper bound by M, which is very easy. You do like this so that it doesn't reach there. Called asymptotic function, right? How to make such a function? You make like an increasing function. Like, how can you make such an increasing function? That's the question. How can you write it down mathematically? So let's try to understand. So that's why we need some calculus. So there's a decreasing function. How to make it increasing? How, let's say this is 1 by x. How to make it increasing? Like how to use this false transformation of this function to make it increasing, like asymptotically increasing. Why minus? Because if you have a height here, you want the negative of that height here. So therefore, if it's y, you want minus of y, right? So therefore, minus 1 by x is such a function. So if you have a function like this, decreasing function like this, the only way to like one of the ways to make it increasing is this. So let's say this example is minus 1 by 1, like minus 1 by x. Now you want it, so this will also work. Minus 1 by x will also work. But let's say you want less than m perfectly. So how to, so here is m. So how to make it less than equal to m like this? Just like asymptotic to m. How to make it? So you just add plus m to it. So that's a new function. So what you make? Your new function is m minus 1 by x. And you assign that to here, each and every ak. So you define your function like this, your sequence like this. It's equal to m if n is less than equal to k and greater than equal to 1. And m minus 1 by n if n is greater than k. And this is your function with finite number, exactly k number of peaks. We have got finitely many peaks. So let's see what are the options. So let's see if it's all right for every point. It's all of them are and one. Yeah, perfect. So now no sequence can have finitely many. This is false. No sequence can have infinitely many peaks. This is also false. So 1 and 2 are false. So let's see the third one. And if 1 and 2 are false, only this can be the option. 3 is true. But we will not do option matching, okay? We will understand what's happening. You can do option matching in exam. That's where you have to be conscious in the options, okay? But let's understand. That's for understanding purposes now. Now, any sequence of real numbers having finitely many peaks must have the property that n is greater than equal to 0 for all n greater than equal to some k. So it's saying that for a sequence having finitely many peaks must have the property that n is greater than equal to 0 for all n greater than equal to some k. If it has a finitely many peaks. Oh, there's also this option too. None of them are true, sorry. So this can be both of them, yes. So why I'm saying this is this, that why you have to understand, like, so what this question is asking, you have to understand. If you think deeply, you will understand that it is asking, does peak and has any relationship with the value of n? But do you think, because peak is a relative thing, right? Peak is all greater than equal to. Even if you decrease all an by the maximum of the all the an, still it will hold, right? So what they're asking is that if an is a peak, let's say an has k peak. Now what to do is that you subtract an. Let's say an has k peaks. One interesting thing is that if an has finitely many peaks, that means it is the maximum. An must have a maximum. Why? Because after a certain point, all the numbers are less than equal to a certain number. If an has a peak, finitely many peaks, and after a certain point, all the numbers are less than equal to that number. That means that can number be the maximum. We have to see the maximum till that point, right? Till those numbers. So let's say an has k peaks, this, or this. All the numbers after this, not ak, but let's say ak dash. Till this, it can be 1000 also. After all the numbers are this are less than equal to this. That means among these numbers, among the peaks, there should be some, take the maximum of them. That should be the maximum value of the sequence. That means if an has finitely many peaks, then an has a specific maximum value. So now if an has a maximum peak, what you do is that you subtract an, all the an's minus am plus 1000 or am plus 1. M is the maximum value, let's say. So you subtract that. Then also the relative property of an greater than or equal to ak will hold, right? The same thing will hold. Do you understand? Then also the same property will hold, right? Finitely many peaks, everything is same. So what I mean is this the peak value, the peak definition is a relative definition. Doesn't It is not concentrated on the absolute value of an or ak. It is a relative definition that an minus ak should be greater than or equal to 0. So it doesn't matter what an and ak are, right? So therefore, since you change it to this, an minus ak will still be the same value as before, even if you change like to an dash and ak dash. If you even take this sub, if you change an dash minus ak dash, it will be same as an minus ak. So it will always be greater than 0. Just the relative value has changed. So therefore, this is also not true because this is a relative property and it's connecting relative property to absolute property, which is not true. So that's it. So therefore, you see that once you do a problem like this, of course, in the exam hall, you need to run your machine faster. That's a different thing altogether, but you have time to prepare. And that's where you need to improve and practice and understand. Okay. That's all about it.
If you're enjoying the video, show some love by liking the video and subscribing to the channel. We welcome you again to this passionate community of budding statisticians and data scientists. Let's enjoy the rest of the video. Stay tuned and stay blessed.